Hello everyone, welcome to topic 5.6, reaction energy profile. By the end of this, you should be able to represent activation energy and the overall energy change in an elementary reaction using a reaction energy profile. So what is a reaction energy profile? Well, these are ways to graphically represent a reaction. Instead of profile, you might also see diagram or graph used instead. The y-axis is generally the potential energy that we see here. The x-axis is generally the reaction coordinate, and that is like over the period of time, how is the reaction proceeding. This shows the progress of the reaction. The graph shows the energy of the chemicals as the reaction proceeds from reactants to products, and so the reactants can either start higher than the products or start lower than the products, and these are classified as two different types of reactions as endo and exothermic, and we'll look at those more in the future. Collision theory says for a reaction to occur, collision between molecules must occur with the correct orientation of molecules and with sufficient energy. This energy, known as the activation energy, is determined by the energy of the transition state, which is known as the activated complex. Now, this activated complex has high energy, like it's up there at the top, because it's a transition state. It's transitioning from the reactants to the products. So it's as it's breaking and making bonds. And so this has high energy, and it's because it's in that transition state, it is very unstable. Okay. So the activation energy for a forward reaction is shown as this explanation here. So the activation energy is the energy of the transition state minus the reactants, which we see here. And for the reverse reaction, you actually go the backwards route, and so it's the energy of the transition state minus the energy of the products. Or I think I said that right. Yeah. The enthalpy of reaction, or delta H, which we haven't talked a lot in the past, is the potential energy difference between products and the reactants. So it's described by this. This is going to be expanded upon in later units. For now, know that an exothermic reaction releases energy and an endothermic reaction absorbs energy. So to kind of summarize that, if our delta H, or enthalpy, is negative, that is an exothermic reaction, because the system, the reacting system itself, is losing energy. If the enthalpy change is positive, that is endothermic, because the system specifically that is reacting, and that's not to say it's container, but the reacting system, the reactants and the products, those particles are gaining energy, so it's absorbing energy from the surroundings. So generally, you would see here temperature increase, and for this one, you could see a temperature decrease. And while that seems like counterintuitive, remember the temperature isn't measuring the energy that is being used or released by the system. It's measuring the kinetic energy of all the particles, including the surroundings. So that temperature change is not tied to it. A decrease in temperature is endothermic because it's pulling energy into the reacting system for the reaction to occur. Continuing forward, an exothermic reaction has products with lower potential energy than reactants as energy is released. An endothermic reaction is the reverse, where products are higher potential energy than reactants, and so energy is absorbed. Therefore, an exothermic reaction has a negative enthalpy, and an endothermic reaction will have a positive enthalpy value. The transition state, or activated complex, is the intermediate point between two stable compounds. At this point, the bonds in the reactants are being broken at the same time as the reactant. There's formation of bonds too, so there's both. When reactants collide with enough energy, they can proceed over this transition energy hump, or this state, and proceed to the products. If the energy of the transition state is greater, the reaction will be slower. So if the transition state energy is greater, the rate will be slower because fewer collisions will have enough energy to pass over it. If the energy of the transition state is lower, then we should see the reaction proceeding faster because there are more collisions that have enough energy. Recall that rate law is generally stated as such, where the value of K accounts for the changes in a reaction rate except for changes in concentration. Okay, this includes changes in temperature. So K is temperature dependent. It is also dependent upon a catalyst, which we'll talk about at the end of this unit. These changes can also be represented graphically. We're going to discuss catalysts, as I said, in 511. For changes in temperature, the value of K is dependent upon the Arrhenius equation. It is not tested directly. Remember that changes in temperature are proportional to the changes in kinetic energy of molecules. This does not change the reaction mechanism, so how the reaction proceeds, so the steps involved. So the energy of the transition state remains unchanged. So when we change temperature, it does not change the reaction mechanism. So the transition state stays the same. Instead, a different value of K can be accounted for by a larger proportion of molecules that have enough energy to react or get over the hump. So the activation energy doesn't change. However, as I increase the temperature going from the red to the green line, right, I see that the area that's under the curve increases each time I increase that temperature. So I have more particles that are able to react. So I have more that are able to climb the hill or climb the mountain. Conversely, catalysts change the reaction pathway, right? So they actually make this hill or the hump lower. So they lower the activation energy. This often results in a multi-step reaction pathway. So they change the mechanism, right? Calculations, just as a clarification, involving the Arrhenius equation, which are here, is beyond the scope of the AP exam. However, that is what that equation is, where A is a constant called a frequency factor based on how often they collide. And then E to the negative activation energy divided by RT is a value between 0 and 1 that represents the fraction of molecules that have enough energy to reach the activation energy barrier with each collision. Remember that EA is the activation energy, R is a gas constant, which is given here, and then T is the Kelvin temperature. However, once again, this is beyond the scope of the AP exam, so don't sweat it. Just know how it works. Temperature will change the number of particles that are able to react, so K changes. Catalyst will change the reaction pathway. So let's look at the ideal. Sketch a reaction diagram for an endothermic reaction. Well, with this means that products will have a higher, because it's absorbing energy, so they will have a higher potential energy than the reactants. So if I draw my reactants wherever I draw them, and just to like be normal, kind of pick a decent one, this is my reactants, and so my products then must be higher, and then I connect them by drawing a hill, and that is it. And label products. Okay? On the graph below, you're going to draw a reaction energy profile of a reaction with the following, and it's listing here. So it says reactants are at 20 energy, so 20 kilojoules per mole, so that's here. The products are at 50, so 40 and 60 are here, so I want halfway between that, so I'm going to draw them here. So my reactants and my products, and then my transition state, it says, is at 80, so about halfway, I'm going to make sure my hill peaks at 80. So then I just connect them. Cool? And that is all you do, where this is 20, this is 80, and this is 50. Okay, so using this as a model, please complete the You Do questions, check your work, and thank you for tuning in.